Hi friends, today we see about the fluid flows. Fluid flow. The first one is the laminar flow. It is one in which paths taken by the individual particles don't cross one another and moves along a well-defined path. The laminar flow is characterized by the fluid flowing in smoother layer of lamina. This type of flow is also known as streamline or viscous flow because the particle of fluid moving in an ordinary manner and retaining the same relative position in successive cross sections. Examples: flow of oil in measuring instruments, flow of blood in veins and arteries. This is a diagram. So, in laminar flow, straight line, the flow in a straight line. Next one is turbulent flow. It is the flow in which fluid particles move in a zigzag way. It is characterized by continuous small fluctuation in the magnitude and direction of the velocity of fluid particles. It causes more resistance to flow, greater energy loss, and increased fluid temperature due to greater energy loss. Example: high velocity flow in a pipe of large size. So large size pipes having facing this kind of flows, turbulent flows. Then Reynolds number. So actually the Reynolds number preferred. It's a dimensionless number. It's applied dimensional analysis on variable and introduced dimensionless number called Reynolds number. It is given by the following equation. Determine the flow is laminar or turbulent. So Reynolds number is equal to rho Vd by mu, or simply we can convert into Vd nu, where density, rho is the density of fluid, V is the velocity of fluid, d diameter of pipe. So nu kinematic viscosity of fluid. So mu is equal to absolute viscosity of fluid. The experiment showed that the flow is laminar when Reynolds number is less than 2000 and turbulent the Reynolds number is greater than 4000, and for Reynolds number in between 2000 and 4000 the flow is in transition from laminar to turbulent. It is always desirable to maintain laminar flow in hydraulic system because the chaotic turbulent flow causes more energy losses. Next one is Darcy-Weisbach equation. The energy loss due to friction in hydraulic system results a loss of potential energy. This potential energy leads pressure drop or head loss in the system. The pressure or head loss due to friction in pipes carrying fluids are deriving using Darcy-Weisbach equation. So HL is equal to 4FLV square by DT. So HL is equal to head loss, so F friction factor, length of pipe, D inner diameter, V velocity of flow, G acceleration due to gravity. So during laminar flow, the friction is relatively independent of the surface condition of the inside diameter of pipe. The friction factor for laminar flow can be found out by the equation F is equal to 64 by Reynolds number when Reynolds number is less than 2000. But in turbulent flow, friction factor depends on both Reynolds number and the roughness of the pipe. American engineer Moody documented the experimental and theoretical investigation on the loss of friction in pipe flow in form of diagram. He showed the variation of friction factor with the governing parameters, namely the Reynolds number and relative roughness, 7 by D. Modi diagram employed for predicting the value of friction factor in turbulent flow. Next is losses in valves and fittings. Pressure drops are also due to valves, expansion, contraction, bends, elbows, tees, and pipe fittings. The losses in valves and fittings in hydraulic system are frequently computed in terms of equivalent length of hydraulic tube. Equivalent lengths can be substituted in Darcy-Weisbach equation to solve for total pressure loss in the system. The formula for computing equivalent length is, so LE is equal to KD by F. So K, factor of valve and fittings. Some of the factors given here. So valve and fitting. The factor is a global valve full open 10, half open 12.5, gate valve full open 0.19, so half open 4.5. Check valve this Papa type 3, then ball type 4, return burn 2.2, standard T 1.8, then standard elbow 0.9, so 45-degree elbow 0.42. When we are considering hydraulic, the Pascal law is a major rule because of pressure. This law states the pressure generated at any point in a confined fluid place, act equally in all directions. Consider two oil containers both in cylindrical form and connected together. Contain some oil. Both cylinders have piston having differences, say D1 and D2 respectively, where D1 is smaller than D2. If a force F1 is applied to smaller piston, then this will produce an oil pressure P1 at the bottom of the piston. Now the pressure is transmitted through the oil to a large diameter piston 2. Because the piston 2 has larger area, the pressure at the bottom of the piston 2 will be P2. Now the pressure P1 will pushes the piston 2 to increase an output force F2. According to Pascal law, P1 is equal to P2. So we can return pressure into F1 by A1 is equal to F2 by A2. So we can change F2 as a maximum force. So we can interchange F2 by A1 is equal to A2 by A1. A1 area of the smaller piston and A2 area of larger piston. Then continuity equation. It states that if a fluid is added or removed from the pipe in any length, then the mass passing across different sections shall be same. So A1 V1 is equal to A2 V2. Bernoulli's equation, it states that in an ideal incompressible fluid, when the flow is steady and continuous, the sum of potential energy, kinetic energy and the pressure energy is constant across all cross sections of the pipe. So Z1 is a datum. So V square by 2G is a velocity hertz. PBW is a pressure hertz is equal to Z2 plus V2 square by 2G plus P2 by W. So this is the thing. We should follow these things.